David Gutzler.
Well, that should have been the last talk of the meeting.
Sorry, Dave, I blew it.
No, that's quite all right. I'm pleased that so many of you are still here, and doubly pleased that I have an opportunity to speak. It means a lot to me. Like many people before me, I owe a lot to Shukla for the simple reason that he hired me back when I was finished my master's degree and was hired to work for Sigma Data Services Corporation, a good Beltway bandit at what was then called the Goddard Laboratory for Atmospheric Sciences. My title was computer programmer, which I'm not sure is a job title anymore, but Shukla proceeded to treat me like a postdoc, and with perfect hindsight, I realized just how extraordinary that opportunity was, and it has meant a lot to me for the duration of my career, that he allowed me the freedom to explore scientific problems to the extent that he did, and I'm very grateful. So I now live in a place where we think we have a monsoon, and so I've spent a fair amount of time cribbing ideas that have come about from the monsoon in an attempt to help out in a place where there's low seasonal prediction skill. And I'll tell you a little bit about that here in the next few minutes. For I believe the third time today, actually one of the advantages of going almost last, advantages or disadvantages, is almost all my punchlines have already been stated, so I can blitz through this quickly. We're looking for repeatedly at this Han and Shukla diagram, which is this left-hand panel, and we learn a few things from that. It's got a sample size of 9, so 9 years, and as Shukla himself pointed out earlier today, the axes are flipped, so we learn, how to do clever things with graphics in order to make a point. And as has been said already, this is figure 1 from that paper, and it's the only figure in that paper. So it's really a tour de force of creative insight. And we've already seen Anjali's figure as well, and she did a very nice job explaining that things maybe are not quite so simple as what you see on the left, and I won't repeat that story either. There's a long history both preceding and succeeding these diagrams of work on land surface summer rainfall connections associated with the Indian monsoon. So here on the left, I've done my best to try to convince you that maybe we have a monsoon in North America as well. So it's just the seasonal cycle of precipitation at Albuquerque. Those are the blue bars. That's where I live. And it's that blue square in the upper right panel. And I've compared it here to Varanasi, which is the red square in the right panel. And you arguably might say that one of the principal qualitative differences here is that we're not quite so purely monsoonal in Albuquerque, where we are not totally out of the winter storm track, but there is an abrupt onset to the rainy season that we can identify, and things actually look like they line up pretty well, at least until I attach units to the plot. And we'll quickly get past that because there's about a factor of 5 difference in the rainfall rates. And so what we don't get in Albuquerque is the summer deluge that you might expect in a place like the Ganges River Plain. Nevertheless, knowing some of the history of Blandford and Shukla's work and others, Tim Barnett as well, one of the first things I did when I moved to New Mexico was to see if we could reproduce the snowpack summer rainfall connection, and here it is. We had this time 22 years, I think, of data rather than 9. an index of spring snow that had already been nicely worked out. I could look at July and August precipitation across the state of New Mexico and line them up, even without flipping the axes. There's a statistically significant negative correlation there, just the way you might expect from previous results, and that all seemed really promising. In the same paper, we pointed out something that has confounded us ever since, I think, which is that there is, just as in the South Asia, there's an ENSO connection as well. So if you do a lag correlation between a wintertime index of El Nino and then look at precipitation in the southwest United States at lag, you see a positive correlation in the winter. Those are the first few months here. And that's what we expect. That's just what has been identified for ever since Ropolevsky and Halpert showed us in the early 80s that El Nino helped shift the winter storm track southward across southwest North America. What was a little more interesting for this paper was that this correlation didn't simply decay down to zero in the late spring, but it actually went negative. And so we have been trying ever since to understand how there might be an ENSO correlation in the summer with the negative sign. One explanation was that, well, what El Nino does is create excessive, or the ENSO cycle creates anomalies of snowpack that then influence the summer monsoon subsequently in the way that Blanford and Hahn and Shukla and so forth have explained. Or there could be a more direct relationship with ENSO, and we're still arguing over that point 20 years later. One of the things that provided a little cautionary tale here, and this again echoes things that Anjali said earlier today, is that if we look at a longer data set and do a fancier data analysis, what we find is a statistically significant negative correlation between this time snow depth and summer rainfall, which is the x-axis. And there's some indication that that in some decades, represented by the open circles on the right, that correlation tends to go away. So we might say that the snow-summer rainfall correlation in Southwest North America is decadally ephemeral. An explanation that requires fewer syllables that some people might like is that it's just not robust. More recently, I won't show it, but the folks at the Tree Ring Lab at the University of Arizona have actually come up with a seasonally discriminating tree ring reconstruction that goes back centuries, and they too find that there are decades where there seems to be an out-of-phase relationship between winter and summer precipitation as recognized as taken up by the trees, and then we go through periods of time when they're out in phase and other periods when they're out of phase. So a mystery there that's still existing. Well, the obvious way to try to sort this out would be with dynamical models. And so in the early 2000s, there was a big campaign called NAME, the North American Monsoon Experiment. And I and some others carried out some modeling and assessments both before and after the NAME field season in 2004. This is the figure from the second paper that came out after NAME, in which we tried to use models in hindcast mode to look at various aspects of climate during the NAME field season in 2004. And what we found was an extraordinarily rich spectrum of phenomena that models could capture somewhat that echo lots of things we've already heard at this meeting. So there's a beautiful diurnal cycle signal reminiscent of the things that Mike Wallace showed us yesterday, with precipitation popping up over the core of the monsoon region, which occurs here over the Sierra Madre Mountains in northwestern Mexico, and a apparent wave of convection that propagates offshore. The models get that one actually pretty well. There's more convection that seems to propagate off the crest of the mountains inland over central Mexico. The models don't do that very well. We learned that there are big problems or at least uncertainties with models. And so these figures on the left represent almost spaghetti diagrams of models these are atmospheric models, I should say, given a prescribed SST to get both the seasonal cycle of precipitation across the monsoon season in either global models or regional models nested within global models. We learned that it wasn't that easy to do nested regional modeling. For example, the models give us wildly different answers depending on whether you put the southern lateral boundary to the north of the south or the south of the ITCZ. We learned that there were often big biases in the seasonal cycle in global models that had to do with the placement of the subtropical high, etc. And we learned that not only is modeling a challenge, but here are 3 different estimates that are probably a little bit hard to see of observations. And so even in 2004, our ability to define what the right answer is in terms of precipitation is difficult. We have a rain gauge-based network, a satellite product on the right, a blend in the middle, and there was a special denser network of very low-tech buckets basically put out in the core monsoon region called NERN. And so the variations among different observational products was not quite as great, but almost as great as the difference between the models. So we learned an awful lot in NAME, but we learned almost as much about what we still don't know as what drives the North American monsoon and what might we do to predict it better. More recently, we've managed to make the picture a little bit more confusing just by looking at something else that again came up just because guys like me noticed that during high wildfire seasons, we seem to have suppressed summer precipitation. So in the upper left is a time series of wildfire activity in the Southwest. Springtime is wildfire season in the Southwest. Monsoon onset, as we define it, marks the end of the wildfire season, which is one of the things that would be really crucial to predict if we could, because the Forest Service deploys its assets in the Southwest, and when fire season there ends, they move their assets up to the Northwest when the fire season starts there later in the summer. We've had a huge increase in wildfire activity over the last couple of decades, driven both by climate and by a century of fire suppression that has changed the nature of the forests and made them much more susceptible to big fires. And what we find with a very simple analysis is that I can take a regression of summer precipitation determined from antecedent ocean temperature and snow cover, and draw a one-to-one line through the regression versus the observed precipitation, which is sort of an estimate of how well we think we can forecast the monsoon. That's determined by the green dots. By the way, these green dots represent a correlation with observations of about 0.5, and my claim is, number one, that is statistically significant. If you make that claim in a journal article, it's true, but I'm not sure it's usefully significant for forecasting purposes. There's the spread of green dots around the one-to-one line, which effectively is what you would predict from that regression. If we take these high fire years and just plot them on the same diagram, they're over here. They're low precip years. So in fact, there is some tendency, maddeningly, and typically it's not perfect, that the high fire years are low precip years, and moreover, almost all the high fire years lie to the left of what you would get from the regression, which means that your regression based on antecedent SST and snowpack is overestimating what actually happened during the high fire years, which is consistent with the hypothesis that the aerosol forcing may be stabilizing the climate, the atmosphere during the high fire years. And then we can then show beyond that in fact this isn't just, that there really is a direct aerosol effect by correlating time series of carbon aerosols, which we know to be of biologic origin, and they too represent a correlation with precipitation. over there. So we have all these forcings, and I can make a case that any one of them is statistically significantly correlated with summer precip, but we still have marginal prediction skill in the southwestern US in the summer, and perhaps here's part of the reason. If we simply look at the autocorrelation from month to month of precipitation in the southwest, we get 0.2, 0.3 most of the years, except in the summer when it's 0. So there is effectively no correlation between month to month precip anomalies in the southwest. And which makes me wonder what the prospects are, what the meaning of a seasonal precipitation anomaly is, but that is typically what we try to forecast. So here's the current NOAA operational seasonal outlook, and it shows projections of slightly enhanced odds for above average precipitation. That's the green blob there centered in the Four Corners region. But most of our process-based understanding, to the extent that we have it, is based on what might affect monsoon onset, which is yet another point that's already been brought up today. So this is the part of the talk where I explain how to tie all those loose threads together and explain that the problem is solved. Are there any? No. But I'm not going to do that. We're still working on it, and in fact, we just have lots of questions. I'm still not sure how much predictability at all there exists for seasonal precipitation in the Southwest, and we need better models in order to do that, which is another point that Shukla's been making for years and years. We should ask whether interannual variability is governed by a single primary climatic boundary condition. Jim Kinter put up a question for the panel that asked whether we could understand how models respond to forcing, and I think that's the wrong question, because I think we do have a pretty good understanding in a partial derivative sense about how models respond to forcing. From a prediction perspective, it's how models respond to forcings in the presence of natural variability, and that's the hard part. I really do think there is a snow cover signal. We can show that in models. There's some statistically significant, even if somewhat ephemeral, evidence for that in the data. But how we put all the different forcings that we recognize together with forcings we haven't yet identified in the context of natural variability, that's what's hard. And maybe we ought to think about what our seasonal prediction target ought to be. If it's going to be hard to predict seasonal totals. Nevertheless, that's what we do, and from a societal perspective, the point I want to end up with, other than the fact that we're working on a system with very low signal-to-noise ratios, and yet another thing we've learned from Shukla is not to be intimidated by such problems, but this particular forecast here, which came out in mid-March, prompted the plot on the lower right, which is the front page of the biggest newspaper in New Mexico. In middle of March, they hopped on that forecast with encouragement from the local NWS forecast office, and the headline was, "Grab your galoshes." The picture on the front page is not a current picture, it's a file photo from last summer. But people are so eager for rain in the drought-stricken Southwest that they will take a forecast where the odds of a wet summer have been increased from 33% all the way up to 40% and turn it into a front-page story on the paper. Happily, I will be prepared for this promised deluge with my new GMU umbrella. And so I want to thank Jim for that, and I want to thank you all for sticking around. So thanks, Piers.
Time for a question?
Is there any attempt to predict monthly rather than seasonal? Because it's the same problem in Australia.
Yeah.
Seasonal mean, El Nino forced seasonal mean totally unpredictable. Because all the fluctuations are from month to month. Evidently. Yeah. I was just wondering, is there something in the monthly predictability?
Yeah, and the quick answer is I don't think there is in an organized way. There is a small army of people that do their own, seasonal type outlooks. But we are still in an operational mode where we focus on seasonal average precip, and I suggest maybe that's something we ought to discuss.